The second type of problem that you'll see in section 2.2 are proofs where we use what's called proof by cases. This is an example that we developed in class on Wednesday, and I said that we could put these two together to prove something stronger. So let's think about what that would look like. If we're trying to prove the statement written up here, if n is an integer, then n squared plus n is even, then we can start the proof the same way we've started all of our proofs. Let something that satisfies the hypothesis be given. But in this case, we have no extra information about this n. It's just an integer. That's all we know about it. And so where we're used to discussing what we know about the number that's been chosen, here we really don't have anything that we can say. And so that's kind of a clue that we would like to have more information about the example that's been chosen. And so this is where we might want to introduce more information by pointing out that the number that was chosen has to fall into one of two buckets, even numbers or odd numbers. And so that's how I'll proceed. I know that whatever number was chosen has to be even or odd. And so if I give two proofs now, one that covers the number if it was chosen if it's even, and one that covers the numbers if the number that was chosen was odd, then I'll have covered all possible bases. And what I want to show in each case is that the conclusion is true. So the conclusion is the same in each case, but I want to show that if the number that was chosen happens to be even, then it makes the conclusion true. And if the number chosen happens to be odd, it also makes the conclusion true. And so that should sound familiar. That's exactly what we proved in class on Wednesday. You did it as two separate proofs. And so this is what it would look like as a proof by cases, where we just point out that in one case where we had even numbers, and in the other case we have odd numbers. And so basically you're directing the reader, depending on what number they picked, to read one or the other of these two. And obviously any particular number they picked would only one of these would apply. But in each case, the conclusion that's proven is n squared plus n is even. And so our final conclusion is that no matter what, in any possible case you could have, the same conclusion holds. And so therefore that conclusion holds for every integer n. So that's the idea of proof by cases. You might think, well, how else other than evens and odds would we ever see numbers broken into categories? And so let's take a second to think about how we can generalize the idea of even and odd. So the way we defined even and odd felt a little awkward, especially the definition of odd. But what we were really doing there sort of harkens back to the way you learn how to do division in elementary school. So just as an example, let me just do an example of what division looked like. If I were trying to do the problem 73 divided by 2 in elementary school, I might write something like this, where I put a little division symbol in my 73, and I say 2 goes into 7 3 times, and I multiply 3 times 2, and I subtract, and 2 goes into 13 6 times, and I subtract, and I have a remainder at the end. So in the language of elementary school division, we would say that that's the remainder, and that's the quotient. So quotient and remainder. The way that division process works, we know to stop because when the remainder, that number at the bottom, is no longer something that we can divide by 2. So in other words, when it's smaller than 2, that's how we know to stop. And so that means when we're dividing by 2, the remainder is always going to be 0 or 1. And that's why we have the evens and the odds. The evens are the numbers for which this process has a remainder 0, and the odds are the numbers for which this process has a remainder 1. If we think of it that way, then we can generalize this for any divisor. So we're going to write, we're going to generalize this to the division problem a divided by b. And let me just give myself, back up and give myself my room here. So when I'm doing the division problem a divided by b, that's what I'm thinking about here. And when I do that division problem, I don't want to worry about b being 0. I don't want to have to think about dividing by 0. So I'll say b is not 0. When I do the division problem a divided by b, I'm going to get a quotient q and a remainder r. Now, we don't want to introduce division notation for as long as we can possibly help it. So if you take this process that I just went through up here, where I had got a quotient of 36 and a remainder of 1, I could rewrite that as a multiplication statement like this. That's saying that 73 is 2 groups of 36 with 1 left over. So the result of 73 divided by 2 being quotient 36 remainder 1 can be stated in terms of multiplication and addition. And so that'll be my preference. So when I do the problem A divided by B and get a quotient Q and a remainder R, I'm going to say that means that A is B times Q plus R. And a caveat will be that the R has to be a number that's less than B. So a positive number, or at least a non-negative number, less than B. And that's what we saw with our division by 2 case. The remainder had to be a number less than 2. So for example, if you do 17 divided by 5, the quotient will be 3, and the remainder will be 2. And so that, as a multiplication statement, that would be that 17 is 5 times 3 plus 2. 39 is a quotient of 13, remainder 0. So 39 is 13 times 3 plus 0. Okay, so that's how the quotient remainder theorem works. And so here's an example of a proof where we would be breaking into cases based on something other than evens and odds. So the statement is if a number is not divisible by 3, then for that number n squared plus 2 is divisible by 3. So this is a hypothesis statement that is negative, and so we know that's kind of hard to get our heads around. But the division theorem allows us to restate this as a positive, because if I let an n be given that's not divisible by 3, instead of that being a negative condition, I can use the division theorem and think about the fact that when you divide a number by 3, you either get remainder 0, remainder 1, or remainder 2. And so those are the 3 possibilities. But if the number is not divisible by 3, then remainder 0 is not an option. So that means that either if n is not divisible by 3, then n has to look like 3 times the quotient plus 1 or 3 times the quotient plus 2. And there the Q stands for the quotient you get when you do n divided by 3. And you can see how much that mirrors our definition of even and odd. So to finish the proof, I just have to do my regular 4-step proof, but now I do it in each of the cases. So for example, if in the first case, if n is of the form 3q plus 1 for integer q, then I can turn my attention to the conclusion. My conclusion is here. And I can just do pretty much the same thing I've been doing. N squared plus 2 is going to be 3q plus 1 squared plus 2. If I do the algebra there, probably should include it, but I'm going to skip just to get to the part that I want to emphasize here. It will look like that. We might have to look up again at the conclusion to remind ourselves what we're trying to do. We're trying to show that's divisible by 3, and of course we can see that a 3 can be factored out. And so because the stuff in parentheses here has to be a whole number, then I know that this is a demonstration that n squared plus 2 is divisible by 3. I'll just write that in, but I'm going to pause to do it. And so this is what the last line of my proof will look like. And then, again, that only addresses numbers that are the form 3q plus 1. So that would be numbers that when you divide by 3, you get a remainder of 1. So that would be, like, for example, n equals 16 would fall into that category. N equals 7 falls into that category. Other numbers n that aren't divisible by 3 could be things like 8 and 11. Those are different because if you try to divide them by 3, you get a remainder of 2. And so that's what we're addressing here. You can write down exactly the same kind of proof for the remainder of this that we did for the one above. You could go ahead and pause and write it down yourself. but I'll count to 3 and then write it in. And so there's the remainder of the proof for that case. Hopefully you can see that structurally what we're doing in each case is very much the same thing we were doing in our 4-step proof in section 2.1. The only difference here is that I have to do that proof in each of the separate cases. Now finally, there is a little shortcut notation that comes up in math and computer science that I want to point out. When we are breaking a proof into cases like this, we were really breaking into cases based on what the number's remainder was when we divided by 3. So it's not that unusual that that's what we care about from a number. It's not so much what the number is or what the division is, but what is the remainder when the division happens. And so because that comes up often, we have a math notation for it. It's called the mod notation. So A mod B would stand for whatever that remainder is. In computer programming languages, at least a lot of them, they use this little % sign. You would see this in a computer programming language. And those do mean exactly the same thing as long as A and B are positive. There is a little bit of a difference between them when those numbers are allowed to be negative, and if you're a coder, you can poke around and see what the difference is. But we're always going to use the math sense. There's a number of good reasons that we'll do that. And so for example, if I wanted to see what 234 mod 8 is, I need to figure out the quotient and remainder that happens with this division problem. So 234 mod 8, if I work it out, I can give you my calculator. But 234 mod 8 is going to be 29 for the quotient, and the remainder is going to be 2. And so if I wrote that as my multiplication statement, it would look like this. 234 is 29 groups of 8 with 2 more to be added to complete the group. And so the mod notation just picks up on the remainder. So we'd say 234 mod 8 is 2. 187 mod 11 is 0, and that's just because I happen to know that 187 is 17 times 11 with no remainder. So getting an answer of 0 to a mod question means that that's a divisibility statement, really. Negative numbers are where the math version of mod and the computer science version of mod are going to differ a little bit. So again, we're going to stick with the math version. And the math version is that we're going to stick to these kind of equations that we can write over here. So negative 23, this will feel a little unnatural, but if I have to write it this way, minus 23 is going to be minus 4 times 7, because that goes a little bit below minus 23, and then I need to add back 5. So in order to have a positive number here, in order for that to be positive, the only way to fill this in is with a positive 5. And we're always going to insist that the answer to a mod question is positive. And then finally, there's nothing magic about whole numbers here. If I can write something that looks like algebra in this form with the quotient and remainder, then I can make a conclusion about that as well. So in this case, for example, 6k squared plus 5 is 3 times 2k squared plus 1 plus 2 more. And again, this puts the remainder in the correct range. It has to be a number between 0 and 3, but not as big as 3. So I can say that 6k squared plus 5 is going to be, mod 3 is 2, because this algebra expression is true. So there are more examples in the homework and more problems for you to try to make sure you're interpreting all these things correctly. So hopefully you can have a look at that and feel like you are understanding and using mod notation correctly.